Okay, great. First of all, welcome everyone. It's my great pleasure to welcome everyone to this HKLF focus group for young scientists. So just to introduce myself, I will be the moderator for today. My name is Otto Hannuksala. I'm a research assistant professor at the Chinese University of Hong Kong, specializing in gravitational wave data analysis. I would like to welcome and introduce also our guest host, Professor Simon White. So it's a great pleasure to have you here. Simon White is a 2017 Shaw laureate and a emeritus director at the Max Planck Institute for Astrophysics, where he served from 1994 to 2019. He's also a research professor at the University of Arizona, guest professor at the University of Durham, and an honorary professor at the Ludwig Maximilian University in Munich and at the astronomical observatories in Shanghai and Beijing. So Professor White is very known for his contributions to our understanding of galaxy formation and for his role in helping establish the lambda CDM model, which is the current standard model for the evolution of the cosmic structure. So welcome, Professor White. It is a great pleasure to have you here. And to welcome also the three participants. We have Zhang Kai-He, who is a Master of Philosophy student in physics at the Chinese University of Hong Kong also. We have Adrian Zhang, who is a postdoctoral research associate at the University of Illinois, Urbana-Champaign. And then we have also Alvina Ye Lian on, who is a NCTS fellow in Taipei. So thank you everyone for coming. I think it's a great pleasure to have you here. I hope that the session will be very fun. So we will be starting off sort of with individual presentations from some of the younger participants here. So we're very much looking forward to hearing from you. So just as sort of to say a little bit about the kind of format for the presentations, we'll have short presentations and then just completely informal, free exchange where we can discuss and you can freely ask questions and share ideas. And so it's hopefully going to be a very fun event. Maybe we could start by the first presenter, who is Zhang Kai-He from Chinese University of Hong Kong. So I think everyone's prepared a short kind of intro into their research, and then we'll take a little bit of time to discuss and ask questions. And of course, we'll also have Professor White here to share a little bit of feedback and ask questions from you. So thank you very much. And Zhang Kai-He, whenever you're ready, you can start sharing screen.
Okay, hello everyone. I'm Zhang Kai-He, and right now I'm an MPhil student in the CUHK. And today I would like to share how the line of sight magnetic field structure can actually lead to the polarization hole. So in star formations, there are actually three very important elements, and they are gravity, turbulence, and also the magnetic field. And today's focus will roughly about the magnetic field. While it is very difficult to observe the magnetic field structure in the molecular cloud, and nowadays observations usually depends on the polarization from the aligned dust ring to imply the B field structures. So the background starlight should be initially non-polarized. However, dust grain in the molecular cloud usually undergo alignments where the dust grain shorter axis should line up with the magnetic field. So when the background starlight passing through the dust grain, it will be blocked by the longer axis of the grain. And as a result, we will observe a polarization when we look at the molecular cloud. So a very common phenomenon in the polarimetry in the star formation region is called a polarization hole. So the figure here on the left is the Serpent's Ring observed by JCMT Pol 2, and the green segment here represents the degree of the polarizations. So if we're focusing in the denser regions, we can actually see that the length of the segment is getting shorter and shorter towards the dense core regions. It means that the degree of the polarization drops towards the increasing density. And this is the phenomenon named as the polarization hole. So a very common explanation on the polarization hole is the dust alignment efficiency will actually decrease with the increasing density due to the high density and the high temperature in the denser regions. So for example, Perdon in 2001 suggested the dust grains are no longer aligned when the fissile magnitude is larger than 3. However, some later studies actually show that this famous argument for the polarization hole may not be a full picture. So the left plot here is the NGC 1333 IRAS 4A, and it is observed by the Sharp single dish telescope. And we can clearly see that a polarization hole phenomenon is occurred in the dense core regions. Again, the red segment here represents the degree of the polarizations. However, Lee in 2014 find that if we use an interferometer, the SMA, to zoom in the core region of these star formation regions, we can actually see that there is a larger degree of the polarizations. And if the grain alignment efficiency is the root cause of the polarization hole, then even if we use an interferometer to zoom in the core regions, we should not observe a larger polarization fractions. So it seems that the low grain alignment efficiency is insufficient to explain the polarization hole. We may actually need something more, and my hypothesis would be the line of sight magnetic field structure will actually result in the depolarization in the core regions. Magnetic field near the denser core regions are actually more tangled and more random. So when the line of sight passing through the dense core regions, we will actually observe a lower degree of polarizations. When the line of sight passing through the surrounding region in the molecular cloud, we would expect to see a stronger degree of the polarizations. But why the B field can be more tangled and more random in the dense core regions? A piece of the evidence comes from the cloud simulation results from Zhang et al. In 2019. So in the left plot, according to Zhang simulation results, you can see that a higher density it is in the molecular cloud, a higher B field offset will result. And on the right plot here, a higher density regions usually shows a higher alpha match number, which indicates a higher turbulent velocity is in the high density regions. So this also shows a positive correlation between the alpha match number and the B field offset. And this gives some of the evidence why the B field can be more tangled close to the core regions. So let's talk about what is the methodology in my research. So I performed the analysis on the 3D cloud simulations to get the degree of the polarization as we can have in the observations. And this 3D cloud simulations is actually a simulation result from one of my senior group mates called Zhang. And this simulation data is solved by the 3D isothermal ideal MHD equation with the self-gravity. The main difference between this simulation data and the previous one from the Zhang data is the duration of the turbulence driving. So for Zhang's simulation data, it keeps the turbulence driving and then it turns on the gravity in a certain time step. While the data that I'm using divide the simulation into two stages. The first stage, I keep the turbulence driving. My senior group mates keep the turbulence driving in the first stage, while in the second stage, the turbulence driving is stopped, but then the self-gravity is turned on. So inside the simulation, cloud simulation data, we are able to identify 3 blank clumps where the star formation regions is very likely to occur there. And our next step is to assume the grain alignment efficiency is perfect, and we will observe the cloud in different line of sight. So remember, in the real observations, we are not able to observe the B field directly. But in simulations, we can actually get the B field strength and B field direction in each position or in each pixel. So by choosing the line of sight that we want and also choosing the plane of sky pixel, we can actually calculate the degree of the polarization through the Stokes parameter as what we can observe in the reality. So here is a quick result. So the left plot here is an illustration plot of how the plane of sky map of one of the bounded cones look like along the z-axis. The red line here is the density contour, while the color in the background represent the degree of the polarizations from 0 to 1. And on the right-hand side plot here is the degree of the polarization against the column density in different line of sight. So you can see that we are able to recover the depolarization trend with the increasing density. And this also suggests that the grain alignment efficiency is not necessary to explain the polarization Hall phenomenon. And one more interesting phenomenon is that with a larger angle deviate from the mean field directions, a less significant decrease in the polarization is observed. And this is because along the mean field directions, we are not able to see the general field structure. The remaining field are thus more random and tangled, and we should see a significant drop in the polarizations. And that is the end of my presentations.
All right, thank you very much for this very nice presentation. I think it's extremely interesting. I certainly have some questions, but let me first maybe give the floor for everyone to ask questions, especially I would welcome the guest host if he has any questions to also interact with the students.
Thank you very much. Your talk was very clear, and I thought it was interesting. You didn't mention observational effects like blurring by the telescope. It seems to me that some part of the effect might be due to the fact that of the finite resolution of the telescope. So close to the center where the directions change rapidly, then you might reduce the apparent signal by averaging in different directions. So have you looked at this? Can this explain some part of the observations?
Yes, actually, because the time limited, so I cannot give a very detailed explanation and a detailed description about the result. And actually, we find that yes, the telescope resolution is matters to and affects the degree of the polarizations when we do this analysis in the simulations. But we find that even if we choose even if we simulate the telescope resolutions, so like in simulation, we can choose the plane of sky pixel to be 6 pixel or even larger pixels. So to simulate a higher resolution of the telescope. The depolarization trend will still remains, but it does affect the structure. When we increase the resolutions, we are able to see the decreasing slope is less significant. But I haven't prepared this in my slide, so I cannot show a quick response here. Yeah.
Oh, no, that's fine. Thank you very much.
All right. Thank you very much. Again, Zhang Kai. So I also had a quick question. I found the presentation very interesting, and I also watched the quick flip a little bit in advance as well. I was sort of curious. This is very much sort of outside of my field of expertise. But you were showing this figure of the NGC 133 and how it was sort of disfavoring the hypothesis that by having a large density or large temperature that the dust alignment efficiency would go down. Could you maybe expand a little bit on how the graphs here show or that how they actually disfavor the hypothesis that these large density areas would decrease the dust alignment efficiency.
Okay, so if we assume that the dust grain alignment efficiency is actually the root cause of the polarization hole, so even if we use a stronger resolutions that we have just talked about, using a telescope with a stronger resolutions, or even using an interferometer to zoom in the core regions, those dust grain should still not align. Yeah, so we should expect to see a similar degree of the polarization fractions as the single dish telescope would observe. But from the result here, using an SMA, so using an interferometer, and also using a single dish telescope, we will find that using an interferometer, we actually observe a higher degree of polarization fractions. So it seems that the dust grain is not necessary to explain the polarization hole. But then, again, because of the time limit, I actually skipped some of the informations. So you can see that from my result, a very quick look at my result here, you can actually find that in the low column density regions, my degree of the polarization fractions is extremely high, nearly 100% of the degree of polarizations. And this is, of course, impossible in the reality, in real observations. So here, my idea is we will actually need the hypothesis that the line of sight B field structure to help depolarize in the high density regions. But in some sense that we may still need the dust grain alignment in efficiency also in order to recover the full picture in the observations. So the inefficiency of the dust grain alignment may not be the single reasons that having a polarization hole.
Okay, I see. And so to rephrase that, the reason that the NGC 1333 measurement was sort of disfavoring is because when you go to the higher density region, if the dust alignment efficiency was dropping as a function of density, what we would expect is that the polarization field here would decrease, but what you actually see is that it increases. Is that the sort of correct physical intuition?
Yeah.
Okay. And then in your case, it's because of the tangled magnetic fields that you would have sort of additional polarization. That the efficiency of the polarization would go down because of tangled.
Along the line of sight, those entangled magnetic field will cancel each other. So we will observe a decrease in the degree of the polarizations.
Okay, very, very, very exciting. Okay, I don't want to sort of hog the discussion too much, and so let me ask for questions, invite feedback and comments from the audience or the other participants as well.
Hello. I have a quick question actually. So if I understood correctly, the polarization hole is a decrease in polarization that we see near the cores of these molecular clouds. And it could be due to tangled magnetic fields that's causing this depolarization. But as far as I know, maybe I'm wrong, the cores of these clouds are usually areas where the density is higher. So isn't it sort of like a competition between the magnetic fields and the density that's leading to the level of polarization that we see at the end? And it's hard to tell which is the dominant factor that's causing the hole that we see. Would that be correct to say?
So sorry, I don't quite get what the competition between from the magnetic field and also.
Yeah, so you mentioned in one of your slides that there are different factors that contribute to polarization, right? So you have like turbulence, gravity, magnetic field, these are all the ingredients that are acting in the cloud.
Yep.
I suppose like all of these ingredients would also contribute to the polarization that we see or do not see. So I wonder if we are able to tell, or at least from your work, which factor is the dominant one that would contribute to the polarization. Because like you said, in the core, we expect more tangled magnetic fields, right? And if the magnetic fields are more tangled, we expect more flipping and then maybe more depolarization, hence the hole, if I understood correctly. But for these areas which has tangled magnetic fields, I suppose these are also the areas where the density is higher, because we're talking about the core or the clumps of the molecular clouds. And if I understood correctly, these are the areas which has higher density. So with higher density, we would expect maybe a stronger polarization, which would be something opposite to what the tangled fields would be doing. So in some sense, the density and the magnetic field would be fighting each other, right? In some sense. So I wonder, how can we tell that it's which factor or which ingredient is the dominant one that's acting at different areas of your cloud, for example, not just the magnetic fields.
Yeah, that's true. So in the dense core regions, especially the gravity actually also take a critical role to tangle the magnetic field also. And so my idea is, so no matter it is gravity or the turbulence that compress the B field, this is all the but as you mentioned, I could in my work I couldn't identify which is the most important ingredients to tangle the magnetic field, but those gravity and turbulence are the factors that can tangle the magnetic field, and this tangled magnetic field phenomenon is able to lead to this observation phenomenon called the polarization hole, and that is what I proposed.
And are these polarization holes common in molecular clouds? Do we see it in a lot of clouds, or is it just a few?
No, it's a very common phenomenon. Usually happens in the molecular cloud.
Okay, good. Okay, thank you.
All right. Thank you very much for the discussion. I think this is very, very interesting. So in the interest of time, I think we can move on. Thank you again, Zhang. I think it's a very, very nice work. I definitely have more questions still, but maybe we can save it for another time. And so maybe we can welcome the next presenter, who is Adrian Zhang, and he is a postdoctoral researcher at the University of Illinois, Urbana-Champaign. So feel free to take it away.
Hello, everyone. I'm Adrian. My research focuses on black hole ring-down phase and fundamental physics. So first of all, let me talk about what black hole ring-down phase is. Black hole ring-down phase refers to the concluding phase of black hole involved compact binary collisions. For example, the binary black hole collisions that I'm now showing to you. So initially, the two black holes will spiral toward each other, generate gravitational waves of increasing frequency and amplitude. But as the two black holes are close enough with each other, they will form a common horizon. And that common horizon is characterized the formation of a new random black hole. That random black hole will settle down into a stationary black hole through emitting gravitational waves that are exponentially decaying in time. And that phase of having exponentially decaying in time waves is known as the ring down phase. And the frequencies of those gravitational waves are called the quasi-normal frequencies. So why should we care about the black hole ring down phase? Well, because this phase is a very important and efficient probe of fundamental physics through gravitational wave detections. black hole ring down phase concerns the oscillations of the event horizon of a black hole. And right outside the event horizon, we have the space-time of the strongest field strength that we can assess outside the black hole. It is also where we expect Einstein's general relativity likely to break down. And if general relativity is not valid near a black hole, the space-time there will be different from the description by general relativity, and that will lead to different quasi-normal frequencies. That is the oscillatory behavior of the event horizon then predicted. So if we measure quasi-normal frequencies different from the predicted frequencies by general relativity, it may very well be the evidence that general relativity requires modification. And of course, it will lead to a whole new direction into fundamental physics research. So previously, I devised a new analysis of the ring down signal to test the dispersions of gravitational waves near the horizon of a black hole. And I also developed a new analysis to probe the existence of dark matter by analyzing the ring down phase. So to implement this ring down program to probe other fundamental physics, we need to extensively and comprehensively pre-compute the quasi-normal frequencies of a black hole under various conditions. And the calculations are in general extremely difficult because the perturbation or the oscillations of the event horizon of a black hole are governed by extremely complicated and lengthy equations. And unfortunately, right now, the existing methods can allow us to thoroughly explore the frequencies of only limited black hole models. And those methods are unlikely to be applicable if we consider beyond general relativity modifications or the presence of dark matter. So my postdoc research focused on developing a new method to calculate the quasi-normal frequencies of general black hole. And our method essentially relies on spectral functions because of their two nice properties. Firstly, spectral functions are complete, meaning that any well-behaved functions can be expressed as linear combinations of them. And secondly, spectral functions are usually orthogonal, meaning that as we express the function in terms of spectral functions, we can handle the information carried by each term individually and independently. So these two nice features may allow us to greatly simplify the calculations of the quasi-normal frequencies. So the flow of the method is basically as follows. So we firstly express metric perturbations, which are mathematical representation of the oscillations of the event horizon as linear combinations of spectral functions. This procedure is known as the spectral decomposition. We then substitute this decomposed metric perturbation into the Einstein tensor, and then we linearize it. So, and then we can similarly express the linearized Einstein tensor as linear combinations of the spectral functions. And by the orthogonality of the spectral function, the coefficient of this linearized Einstein tensor have to be 0. So follow this route, we transform a set of highly coupled partial differential equations into a system of linear algebraic equations, which are much easier to be handled mathematically. And we found that the eigenvalues related to this system of linear algebraic equations contained the quasi-normal frequencies of the black holes that we are studying. So we first apply the method to the Schwarzschild black hole, which is the simplest non-rotating vacuum black holes in general relativity to validate the method. The blue dots are the eigenvalues that I mentioned. The pores are the quasi-normal frequencies of the Schwarzschild black hole calculated using the existing methods. And the capital N here represents the number of spectral functions included in the computations. As we can see that in general, as we increase the number of spectral functions included, the dots are coincide with the cross more and more closely. So these results prove that the spectral methods allow us to calculate the quasi-normal frequencies of the structure black hole. So we have also applied this the spectral method to rotating black holes. This is an important step because almost every astrophysical black holes that we know are rotating. We found that if we applied our method to calculate the fundamental mode frequencies of rotating black holes of dimensional spin up to 0.25, we can still accurately calculate the fundamental mode frequencies. These modes are the dominant mode frequencies when we detect the rain-down signal. And these are encouraging progress. Right now, we are pushing the method to a more fastly rotating black holes. And my Use Equalism and I are now conducting a series of research to fully developing this method so that we can apply it to black holes which cannot be studied using the existing method. Once we have got the frequencies for black holes in under different conditions, we can compare the calculated frequencies with those measured. And this allows us to test general relativity by observing the oscillations of the event horizon, and we can constrain various alternative gravity theories that aims at modified or complete Einstein's relativity. So we expect that these results will eventually lead to some very interesting results, and you are welcome to contact me at any stage about this work if you are interested to know more. So thank you.
All right, thank you very much, Adrian, for a very nice presentation. So I would have some questions definitely regarding well, one of the things I've always been wondering is the possibility of quasi-normal modes from charged black holes. I would have some questions from dark matter as well, since you mentioned it. But let me open the floor first for questions, either from the guest host or from some of the other participants.
Oh, thank you for the talk. I think this way of calculating quasi-normal modes and finding the frequencies is looks very promising. It's very similar to the way that people calculate stellar oscillations of, for example, initially the oscillations in the sun. I think I'm interested to know what happens when you go to rapidly spinning black holes. I mean, as you say, the simplest case, of course, is the Schwarzschild black hole. I think there are no fundamental issues there, but it seems to me there might be fundamental issues if you take an extreme Kerr black hole. So if you're very close to A equals 1, can you still perturb it, and will the methods work, or do you get divergences? Because, as you know, as you approach A equals 1, you're very close to breaking the cosmic censorship hypothesis. So there may be difficulties in actually even constructing event horizons once you try and place oscillations on top of an extreme Kerr black hole.
Thank you very much, Professor Wright, for your questions. Indeed, we expect that it will be increasingly difficult as the spin, which is the extent of the rotation, increase. I would say that if we are approaching the extreme mode spin limit, we have to be very careful because many singularity would have a reason there. So I'm afraid I cannot make any comment about the performance of the method at that regime right now, because I think our plan right now is to apply the method to rotating black holes that is very close to that limit, but not exactly at that limit. And
perhaps you could already, perhaps you can already see from the way the mathematics behave as a function of your spin parameter A, that there are clearly are singularities as A approaches 1. I mean, does this show up explicitly when you do the analysis?
Yes. But when we do the calculations, we do not expand the equations as in a power series of 8. We solve the exact linearized equations. But as I said, when A is equal to 1, then there will be many more singularities of those linearized equations. So that will definitely be a interesting direction into which we investigate. But right now we are still not sure about the performance of the code there.
I mean, this I think might be interesting for collapse, because collapsing objects get very close to being spin limited just through angular momentum conservation as they collapse. So you might expect black holes formed from collapse to be very close to the extreme Kerr limit, and so the calculations in that limit might be quite relevant.
Yes, we will definitely look into it. Thanks for your advice.
So I had a sort of a follow-up question. I'm also very curious about the extremely rotating black hole, but there is also another possibility, even though in astrophysics it's of course not very common to see this, but according to the no-hair theorem, the black holes essentially are described by 3 quantities, so the mass, spin, but also charge. And I was just wondering, have people taken a look into the quasi-normal modes also of charged black holes? And do you know if they would be very difficult to include in a framework like this?
Well, according to my understanding, yes, some people indeed have looked into the quasi-normal modes of charged rotating black hole, and that's called the Cold-Newman black hole. And the quasi-normal mode frequencies have been calculated, and I think they have also been applied to analyze the detected astrophysical raindown signals. And they found no electric charge of the Raman black hole formed in the LIGO and Virgo events. So that's reassuring. That just means that our assumptions that astrophysical black holes carrying a negligible electric charge is still valid. But regarding the applying this method into that black hole set, sure, we would also like to apply this method to that black holes, because ultimately we would like to validate the method as accurately as possible to the best extent that we can do.
Did these calculations allow electromagnetic oscillations in addition to gravitational oscillations?
Yeah, in principle, yes, because right now we have only been considering metric perturbations and considering the perturbed linearized Einstein equations. But this system of equations can be augmented if we consider the perturbed Maxwell equations in the curved spacetime. In principle, because using the orthogonal properties and the completeness property of spectral functions, this should be fine. But the key difficulty is to estimate the asymptotic behavior of these two types of perturbations at the event horizon and at spatial infinities. But right now, my UI/UC colleagues and I are focusing the method on the gravitational perturbations as a first step. But once we have validated methods, we will definitely apply it to some, let's say, black holes coupled with dark photons. Then that would be very interesting, because it will really probe many new physics, including dark matter. So this is definitely one direction to go. And the quasi-normal frequencies of cold Newman black hole is certainly a bridge that we have to cross eventually. So it will also be a goal of our study.
Thank you.
All right, thank you very much, Adrian, again for the very nice presentation. And so let me also welcome next Alvina to talk about her work. I think some of it is sort of loosely related to also to polarization, and so looking forward to it. Take it away.
So hi, I'm Alvina, and I recently graduated with a PhD in theoretical astrophysics from UCL, and I will actually be starting as a postdoctoral fellow at NCTS Taipei in December. So in fact, I will be moving to Taipei next week. So if any of you happen to visit this side of the world, just let me know, and I'm more than happy to invite you to visit NCTS at some point. So I work mainly on large-scale magnetic fields, and today I'm going to tell you a little bit about my work in progress on radio polarization in diffuse intracluster media. So perhaps it may be useful to see the big picture first, as I suppose all of us here work on different things. So we know that magnetic fields are everywhere around us, but very little is known about their origin and their evolution. So the question is, where did the first magnetic fields come from? And how do they evolve with the structure formation of the universe? And the reason why it is challenging to see and measure the magnetic fields is because they are simply invisible to us, to our eyes, which means we can only infer their properties and their existence through indirect methods. And what we can see in the background here is the beautiful northern lights, and it is an evidence of the Earth's magnetic field interacting with the charged particles that's being carried by the solar wind. So now if we move on to larger scales than our sun and the Earth, the galaxy that we live in, the Milky Way is also magnetized, as well as larger scale structures like our nearby galaxy here, M51, and also galaxy groups like the Stephan's Quintet. However, for galaxy clusters and beyond, it becomes more difficult for us to measure magnetic fields because they're just a lot weaker. However, it is important to correctly infer the magnetic field properties at such large scales because they should hold some evidence of the first seed magnetic fields. So we still don't know for sure whether the first seed magnetic fields are primordial in origin, meaning that it's generated soon after the Big Bang, or maybe the magnetic fields are generated much later on through some astrophysical processes after the first stars and the first galaxies form. So what I'm showing here is an example from the ENSO simulations, and we can see that different seeding mechanisms actually can imprint different signatures in observations. So on the left-hand side, we can see that in the primordial case, the large-scale morphology looks more filamentary, whereas in the astrophysical case, it looks more blobby. So the colors here represent the average temperature and average magnetic field strength from the simulation. Now, observationally, the magnetic field is usually measured through radio polarization. So what we can see in the background of my poster here is a cluster of galaxies. I think this is A3667. It's undergoing a collision in the center and then producing shock waves that you can see as it goes outwards in red. So there has been instances where people find that some radio point sources in the background are missing, or that some radio sources are actually brighter than the others. So in this work that I'm showing here, we're trying to address these questions by carrying out polarized radiative transfer calculations to investigate how the degree of linear polarization of these point sources behind a cluster with a large-scale shock is affected. So what we can see here in the figure is one of our results. The different columns represent the shock when we see it at 3 different inclination angles. And the top row represents the total radio intensity that's being observed, while the bottom is the degree of linear polarization. What we can see here is that the viewing angle actually matters due to Faraday effects. And the level of polarization actually increases near the boundary of the shock, where the magnetic fields are more compressed. So statistically, what this means can be summarized in this panel here. The bright sources, so we have bright and dim sources in our calculations, and the bright sources, we find they hardly experience any change in their polarization. Whereas for the dim sources, they either get depolarized or repolarized. So what we define as dim sources here are the ones that have brightnesses that's comparable or weaker than the line of sight intracluster medium brightness. So some of these dim sources experiences an enhancement in the polarization. So there's an increase in the polarization when there's actually a stronger Faraday rotation that's going on, meaning that the radiation that passes through from the back to the front, so through the intracluster medium, actually experiences an increase in polarization due to the larger thermal electron number density, for example, in the cluster, or that when the cluster has a stronger magnetic field strength, like in the shock that we modeled earlier. And also when you have, because magnetic field is a vector, so apart from the strength, the direction also matters. So when there's like an ordered magnetic field, that would also crank up the polarization. Whereas a portion of these dim sources get depolarized when its radiation is going through regions which are more boring, so nothing much going on. So if they're already very dim to begin with, and they go past the cluster and there's not much going on there, then it may get depolarized. It may be more likely to be depolarized than gaining polarization. So there are 2 possibilities that could happen here. So the take-home message from this work is that when we see radio background point sources which are missing in the radio sky, it is not because that they do not exist. However, they may be more likely to be depolarized by an intervening foreground cluster that's undergoing some intense activity, like the one that I'm showing here, like a merger with shocks, and that some sources may appear brighter than others if it undergoes an enhancement in polarization. So that's all from me today. Thank you.
All right, thank you very much, Alvina, for this very exciting discussion. So let me invite questions from the guest host and the audience.
Thank you, Alvina. These are very interesting topic. So I had a couple of points I was unsure about. Can you show your picture comparing what you call the seed field and the
This one.
This one, yes. So I noticed the 2 simulations here, they differ quite a lot in the gas physics, in the sense that on the left-hand simulation, the gas is non-radiative, so it is unable to collapse. There are no feedback processes. Whereas in the right simulation, the gas was able to cool, make stars, and cause outflows from AGN. So how do you know that the difference in the magnetic field is due to the seeding and not due to all these additional effects?
That's a good question. So, for this part, we're purely looking at the large-scale morphology. So with the primordial case, it's more filamentary, and to my understanding, that's because you just plant a seed magnetic field at the very beginning, during Big Bang, just let it inflate and evolve with structure formation, but without much feedback or any feedback, because you don't really have like AGN stuff going on there.
Well, when I look at these 2 pictures, I see the same large-scale structures, so the same filaments and the same clumps and so on. It's just the clumps are much tighter. So I think that the clumps are tighter because the gas is able to collapse and radiate, whereas it can't collapse and radiate in the left-hand picture.
So I suppose on the right-hand side, because the gas can collapse better because of the later on stages of the feedback from AGN and stars. It also carries with it the magnetic field and actually increases the magnetic field strength. If I remember correctly, the red should be the field strength and the green is probably the temperature. Yeah. So you can see that for the astrophysical scenario, the magnetic field strength goes up to a higher level than the primordial case.
That's right, but I think you should, if you wanted to contrast primordial seeding with seeding by astrophysical sources, you'd have to have simulations where all the rest of the physics was the same. So if you change two things at once, then it's hard to tell what's responsible for the differences. So that was one question I had. The other one was, as I understand Faraday rotation, if you have a background source with a certain degree of polarization and it's monochromatic, so there's only one wavelength, then if you pass through a foreground magnetized plasma, you get rotation, Faraday rotation, but you don't get any depolarization. In other words, the strength, the total flux is conserved and the rotation fraction is conserved, just the angle rotates. So I'm a little confused about what you were arguing here, because you seem to be saying that for a background source, the degree of polarization would also be decreased.
Right. So the example that I'm showing here, so we start off with sources where we fix the degree of linear polarization. So all of these sources that we have, that we just plant randomly behind the cluster. They're behind the cluster. And these sources, there are about 1,000 of them. And we fix the degree of linear polarization to be about 5%.
Okay.
And the cluster that we have in the middle also has its own degree of polarization, and it happens to be about 5 to 6%.
Sorry, is it emitting or is it just a screen?
It's emitting as well.
So you're adding together the light from the background source and the light from the cluster?
Yes.
So maybe the effect is because you're averaging two different things rather than because the background source itself is changing.
So the background source itself, it's fixed at 5%, and then the emission is being tracked. So the radiation that's radiating from the source is also going past the cluster. And when it goes past the cluster, it goes through different radiative processes like absorption, emission, Faraday rotation, Faraday conversion. So it's a full polarized radiative transfer calculation. Well,
absorption is very weak in the normal cluster circumstances.
It's much weaker. Yep, that's correct. That's what we find as well in this calculation that we did.
So then the total intensity shouldn't change much.
Not too much. But what we find is that when the source brightness and the cluster brightness are quite similar. So here we call them the dim sources. The bright ones are about 2 to 3 orders of magnitude higher in brightness than the cluster. And these bright sources don't get affected. So they're so powerful that if it's really bright, it's still seen as really bright at the end.
But that suggests, I mean, after all, the amount of scattering or the amount of Faraday rotation doesn't depend on the brightness of the background source. Right? It only depends on the foreground medium. So what you've just said confirms that the light of the background source isn't being affected by traveling through the cluster except by rotation, but what you see can be affected because you're adding an additional source of radiation on top of it.
Yes. So what's interesting is that some of these dim sources are there, but after going through all these processes, we don't see it anymore. So observationally, we don't see it. So when we take, for example, a picture of the radio sky, sometimes there are empty patches. And these empty patches doesn't indicate that we don't have sources there. They might be sources, they might be really dim ones. They just got depolarized if there's something in between them.
So when you say you take a picture of the sky, you mean in a particular polarization because they're not being affected in their brightness, their total brightness, only say a particular mode of linear polarization.
Yes, the polarized intensity. Yeah.
I think it's an interesting problem.
Thank you very much, everyone, for very nice presentations. I think it's a lot of interesting research that we're doing. So Thank you. And I think now we can move on to the free topic dialogue. And so just to give a preface a little bit, so the free topic dialogue is essentially just a kind of an informal chat. So everything goes, you can banter, share ideas, if you have questions that you'd like to ask about. Not just about research, but also things like experiences in life journey. Then we have, of course, Professor White here, who can share his experience. And so essentially, for the free dialogue, we can have completely free discussion. Maybe I could start off actually, because I have definitely several questions for the various participants, and I'm also actually very curious about some of the questions I would have for also Professor White. So maybe we could kick this off with something a little bit more informal. And I was thinking for Simon White, maybe a question that we could start off with to just kickstart the conversation is how did you end up in doing research sort of very originally? So what sort of motivated you to take up research in the early days?
Well, I think when you ask what you want to do in life, you should first try and find out what you're good at, which you can do by going to university, and you find out, for example, I started off doing courses in mathematics and realized after a while, although I was pretty good at mathematics, there were other people out there who were much better than I was. And so I thought what I'm good at, and then I discovered that I was good about thinking about more phenomenological things, about how things work, how they might work, ways to approach that. And so that took me into a more applied science. So in my case, it was astrophysics. It was almost by chance that it ended up being astrophysics. It could have been other parts. So I think the things that are important are firstly to try and do things where you feel that something you're good at, because you'll be more able to make a contribution. And secondly, it's really important not to think what is going to get me noticed or what should I do in order to get my job, but to do things that you find interesting. Because if you find it interesting, then the chance you'll come up with something original is much greater than if you say, oh, I think this topic is the hot topic at the moment, so I'll go and work on that. Because if you do the second thing, then usually, of course, you'll be in competition with a very large number of other people, which is why it's considered a hot topic. And there's no particular reason why you should be necessarily better than them. Whereas you follow what you really feel curious about and what you're interested in, then your interest will actually push you. So I think that's a very important part of research.
Yeah, no, definitely. And I wonder actually about maybe the participants' experience as well about research. I also had a little bit of a similar story as well. I sort of ended up in astronomy almost by accident. Actually, when I was a kid, what I wanted to be, and my mother always tells me, is that I wanted to be a Zorro. So that was the Spanish swordsman from TV. And ultimately, I decided after a very long time of sort of juggling between different options that after Zorro, I wanted to become a firefighter. And after becoming a firefighter, I wanted to become a lawyer because lawyers make a lot of money. Then I went to high school and I realized that, lawyering seems a little bit boring. And at the same time, I found out about physics, and that's sort of how I also ended up. And this was very much by accident, sort of, for me as well. But maybe I could invite some of the participants as well. If you'd like to either share from your experiences, how do you start your research life, or if you have questions about either even not research related questions, feel free to just speak up.
Actually, I'm interested to know what do you think what are the qualities of a good astrophysicist or a good astronomer need to have in order to really be a good scientist?
You have a very, very formal topic with high mathematical content. So, in your field, aptitude at the mathematical analysis of normal mode analysis, whatever, is clearly critical. But other areas of astronomy, if you want to build instruments, then you have to be good at putting things together and making them work. It's completely different. So I think astronomy as a whole is very broad, and so there are many areas. So as I say, I think the thing which you need in all the fields is first, you have to be good enough at it. So that's why I said you have to identify what you feel you're good at, because that's where you'll make so which aspects and do that. And then curiosity is a very important part, feeling you want to know, how to make an instrument which is more sensitive, or how to do a mathematical analysis which clarifies the physical state of a system better, or take some very complicated set of data and find the regularities in it. There are different areas of astronomy where different things are needed, or to look at some very complicated subject like galaxy structure, and understand where the regularities are. In every area of astronomy, there are different things, but different kinds of aptitudes are needed. So I think you have to feel curious to find out about the topic that you choose, and you also have to have the abilities that allow you to make progress in those topics. And then the other important thing is always to be open to something which is different. If you believe that what you've heard is the way it is, you will never find something new. You always have to realize that actually all our understanding of things is always provisional, and some fraction of it is always wrong. So you need to be open to see the things that can be improved. And that's true for making instruments as much as it is for doing mathematics.
Thank you very much for your advice.
I think I could maybe follow up the question, since you mentioned kind of surprises and scientific discoveries. What would be the biggest surprise you would say that within your career, Professor White, on kind of throughout your career, something that you found particularly surprising or kind of exciting in the years of research that you've been doing? I think it's a very good point that of course many times the biggest scientific discoveries of course come from surprises, so things that we really didn't expect that turned out to be a certain way. So what would be maybe one of the kind of big surprises that or moments that you had in your career that you would say surprised you?
The most striking one is that in the early 1980s, there was actually a measurement from a Russian group from tritium decay that the electron neutrino had a mass. Turned out to be an error. But the mass they came out with was 30 electron volts. And we know how many neutrinos came out of the Big Bang. And if you multiply the number of neutrinos that came out of the Big Bang, which is just a fraction of the number of photons, which we measure directly, if you multiply the number of electrons going by 30 electron volts, you found out this was most of the mass of the universe. So if this was true, then apparently the missing mass problem was solved, and it was all made of electron neutrinos. So we tried simulating this because we know the properties of neutrinos. We could predict what the structure coming out of the Big Bang should look like. We then even very crude simulations in the 1980s to predict what the present day structure of the universe would look like, and it just didn't match. So for us, it was ruling out the only known particle candidate for the dark matter apparently was excluded. So then people immediately, of course, physicists are very creative. People invented lots of other possible candidates. And we tried a simulation with the next simplest one, which was something which came out of the Big Bang, was so heavy it didn't have any motions in the early universe at all, at least not that are relevant. And then that predicted structure, which actually looks quite like the structure which we saw. So that was the origin of the cold dark matter model, which said most of the mass in the universe is a new kind of elementary particle that is outside any of the physics that was known at the time. So this was quite an outlandish suggestion, and basically none of the astronomers believed it. So the biggest surprise was this actually turned out apparently to be the right answer. And so not only have the observational data become much, much better on the distribution of matter around galaxies in galaxy clusters, now in the microwave background from the fluctuations in the microwave background, all this came later, they all fit this interpretation. And then even in the first time we even did a simulation which had a cosmological constant in it. So we had the final lambda CDM model in our first paper, but everyone told us that cosmological constant couldn't possibly be there because it was completely unreasonable to have this value. And so we actually threw it away. And then later, of course, this came back as well. So it was quite extraordinary. The first thing we tried has now become the standard model.
Yeah, that must have been a very big surprise. And today it's also one of the biggest puzzles in astrophysics and cosmology. And so I can imagine that may have been a very big surprise when it came out. So let me also ask, so we've had a chance for Adrian to ask questions as well, but let me ask if Zhang Kai-hei or Albina, if you would like to ask some questions as well. Again, yes. Don't feel shy. This is a very informal discussion. Great chance to discuss.
Yeah, I also have questions, but before my questions, I would like to share some of my experience. So when I was young, I'm already love astronomy. I always have a dream, a very immature dream that I want to know everything, what the cause behind everything. But when I grow up, when I study physics, when I go to the university, and I realize it is impossible for me to know everything within my life. So I have to choose what kind of field that I want to know more. So I participate in that field. I do more research with this. And well, recently I have, so right now I'm the second year of the MPhil study. So recently I've started to worry of my career because I don't know how to say so, but I would say in this academic career is quite competitive all over the world. So I think Albina and Adrian, they are senior than me. They may have already faced it, and also two professors here, you guys have already experienced this process. Do you have any advice for me? So how should I fight for positions, or how do you have any special experience want to share to me or share to others students here? How do you survive in this competitive career? And if you don't mind, you can also share some of your experience about, I suppose you also have friends and also colleagues that finally they do not participate in this academic career. So what will they do in their life?
Well, let me say something here. I think if you look around worldwide at the moment, astronomy and astrophysics has been very successful, and they're pulling lots and lots of young people in as graduate students, and many of them go on to be postdocs. And if you look at the number of young people we have who are all in the first 10 years of study, there's probably 4 or 5 times as many people in this 10 years as there are in all the senior positions, which is sort of the next 30 years of career throughout the rest of the world. So it's clear that most of these people will not get long-term positions. It's just this is the way the numbers work out. So the most important thing to tell our young people is it's not a failure if you end up doing something else. There are lots of other interesting things to do in life besides being academic astronomers. And if you can learn skills, analysis skills, mathematical skills, computational skills, and have fun for 10 years, and then you go and use those skills doing something else, that's not a failure. That's great. And in fact, this is what's going to happen for most of the people. So the most important thing is to not have the feeling that somehow you failed if you don't do this. There are lots of other things you can do which are also very fulfilling in life. So I think this is critical, and this is something which the senior people like us professors have to communicate to the young people like you. You know, we're not educating everybody to be like us. It's numerically impossible. You know, there just aren't that many positions. And if we did want to do that, we should take far fewer students and have far fewer postdocs. Because, you know, since the student and postdoc career lasts 10 years and the rest of the career is another 30, we should have only one student or postdoc for every 3 senior people if you wanted to keep everybody in the field. And that's very far away from what we have. So that's the first thing. And the other thing is, you know, I'm sure you're good. You know, you give a great talk. You have lots of ambitions. Whatever you do, you'll end up being successful. So do what you find exciting and go with it. And, you know, if it goes out well and you're lucky and it comes out well, then you will get a faculty position. And if it doesn't, well, you'll go and do something else and be equally successful at that. So don't worry too much about it.
Thank you.
Do the stuff that you find exciting.
Yeah, I definitely second that as well. Like, I think it is definitely important also to remind people that that the life outside of academia, of course, is also extremely valuable, and so it should definitely not be seen as a failure. And I've always had since you asked about personal experiences, Professor White knows much more about the academic kind of advice, but I can say from my personal experience, I've always sort of chased things that I've always wanted to do, and so for me that's always been the biggest motivation. And I think it has worked out well, and I've enjoyed my research career. I think it's an important aspect to enjoy the process maybe more than sometimes the outcome. All right, thank you very much, Zhang Kai, for the question. Let me also invite if there are quick questions from Alvina.
Probably just to follow up on that. So I guess when I graduated from my PhD, I was like, woohoo, I was really happy about it. And then when I started applying for jobs, then I realized, oh gosh, this is when the real challenge begins, actually. And it might be the sort of lifestyle I might have to face for the next couple of years as I swim in this postdoc market. So it's exciting and it's intimidating at the same time, I would say, to see how things turn out. But I agree. I think during the process, like, we find out what we enjoy, what we're good at, what we don't like, and we also get to try different things as well in between. So let's see how things go. But actually, I have one little science question, since I think we all talked about simulations at some point, but perhaps Professor White can comment a little about this. But what do you think is the biggest challenge in computer simulations to come? As computers get bigger and faster these days, I wonder if the challenge has evolved.
I think that's a great question. So I've been, my own attitude's been evolving, but what I see now, let's say something which I'm involved in, and it's peripherally related to what you're talking about, is studying galaxy formation. And this has become something which is more and more become something which is done through very large numerical simulations, which become very complicated. So, I mean, telescope powers increased by a factor of 10 to the 3 or 10 to the 4 during my lifetime, in terms of photons you can collect per unit time or so on. Computer time power has increased by a factor of about 10 to the 9, both in terms of memory and in terms of computation speed. So the increase in computational ability is enormously more than the increase in, let's say, observational ability in terms of the factor. And a reflection of this is the fact that simulations and computer work is taking a larger and larger part of our field. But I think it brings a complication, particularly with something like galaxy formation, because it now means we can do very complicated simulations, which include the dark matter and the gas and all the cooling processes and the magnetic fields and attempts to do formation of black hole. All these processes you can put into your simulation. Some of them you can actually solve real equations, and some of them you just have to put in as some kind of recipe because we don't understand well enough to do this. So you put it in what's basically a recipe, which sort of conserves the basic quantities like mass and energy, but otherwise is almost arbitrary and has some parameters which you fix. So you have this very complicated simulation with many, many interacting parts. And now you can compare it to a galaxy in the history of galaxies. Galaxies all look different. They're all very complicated. And how you see them depends on how you look at them. They look different in the radio or in the optical, for example. So you have extremely complicated simulation where some aspects of it are arbitrary or very rudimentarily put in, and some parts are probably missing. And you have a very complicated reality where that lots of processes are occurring, but in reality, you only have limited observations. So the question is how do you put together a very complicated but imperfect simulation and a very complicated but imperfect observation and come up with understanding? So I think the hard part is how you get real understanding at some level out of comparing one complicated simulated object with a very complicated observed object. And then I think our field as a whole hasn't really got to grips with this. I mean, people are sort of feeling their way. But there's a tendency, you take some observations or you take partial observations and then you make your simulations until they look like the observations and say you're done. But I think this isn't really true because, we know it's not true because they have people with different simulations with different representations of physics and they all claim it look like the observations. And the physics is different. So clearly they haven't yet got to the truth. And so understanding what we've really learned is a challenge, I think. I don't have a solution.
And I guess that's what keeps us going.
Yeah, but each person tries to understand their bit and they try to make progress, so that's fine. You are interested in the magnetic transfer, radiative transfer through things. Well, that's that's an important part for some aspects of the problem. So work on that and see if you can understand it better.
Okay, so we're running a little bit low on time, and so I would really like to thank everyone for the discussion. I think it was very insightful. I really liked the presentations by all of the participants, so very nice work. And just to sort of move towards the club closing, I would like to invite Professor White to share his advice and encouragement and some of his personal experiences before we close this session. So take it away, Professor White.
Well, I think actually, I've already done this, but pretty much in the previous things. So I think, do the things that you enjoy, the things that you're good at. If you find you're not enjoying it or it's stressing you out too much, then maybe this isn't for you, and there are lots of other good things to do. So don't feel this is a failure. Go on and find out things that you really do like, and be open to new things. I think there are always new things out there. We only have a very partial understanding of everything, and there are some things that we don't understand at all. So if you can help push some corner of this forwards, well, then that's your contribution to the whole endeavor.
Right, thank you very much, Professor White. And so From my side as well, I would like to thank everyone for coming. Thank you to the participants, and thank you for taking the time to make it Professor White as well. And so we are at the end of the session, and so I think we can close up the call for now. And again, thank you very much for coming, and possibly see you in some of the other Hong Kong LF upcoming events. Thank you.